In this video, we're going to look at some aqueous ionic equilibria practice problems, the like of which that you'll see in a general chemistry assessment. So we're given our first question. We have a balanced equation given to us, and we're told it's going to be an ice table type question, and we have some initial conditions. We're told that initially we have 0.2 molar solution of acetic acid. We also have 0.1 molar worth of its conjugate base. So this tells us it's a buffer. It's not an ideal buffer because these are not a 1-to-1 ratio, but we have a buffer nonetheless. And then we're asked to calculate the pH. Now the pH is going to be based on the hydronium concentration reached at equilibrium. So we essentially have to solve for the equilibrium hydronium and then calculate pH. We have drawn lines for water because liquids and solids don't participate in dynamic equilibrium. We know that we initially don't have any acids, so we can say that that's 0. We just have our buffer. So we're going to shift right because we shift towards a 0. So everything on the left is going to decrease by a value x. Everything on the right is going to increase by a value x. Again, that's because we're shifting to the right, because we shift towards 0 as always. And then we add the initial and change molarity. So we have 0.2 minus x. We have 0 plus x, which is just x, and we have 0.100 plus x over here. We're provided with an acid dissociation constant, Ka, so we're told that this is 1.8 by 10 to the negative 5, no units in general chemistry. So now we can solve the expression. We know that it's going to be the product of the products, so 0.100 plus x multiplied by x. So again, the product of these two products, in a 1-to-1 mole ratio, so each raised to 1, a coefficient of 1, divided by the product of the reactants. There's only one reactant that's eligible to be included here. We notice because the acid dissociation constant is very small, typically order of magnitude 10 to the negative 4 or 5, we can probably assume that any shift towards the right is going to be negligible, so we can assume it's 0. So we can make the assumption that this is approximately 0.100x over 0.200. So we essentially ignore the shift x, ignore this x and this x, but we retain that x. So that's an assumption we can make. If we solve for x, then x is going to be 1.8 by 10 to the negative 5 multiplied by 0.200 divided by 0.100. The whole thing is going to have units of molarity. Which will give us 3.6 by 10 to the negative 5 molarity. Before we go on to calculate our pH, we can check our assumption to make sure it's valid. So let's check the assumption. We don't have to check both x's here, we just have to check the one that's most likely to fail. The one that's most likely to fail in this case is the smaller total value, which is the numerator. So my x that I ignored is 3.6. by 10 to the negative 5, and I ignored it from a total of 0.1, and I want to see what that is as a percent. Now, the goal is I want it less than 5%, and I can clearly see 10 to the negative 5 divided by 10 to the negative 1. Well, that's roughly going to be 10 to the negative 4. And then I would multiply this by 10 to the 2, which is going to be, sorry, that's going to be 10 to the negative 6, rather. Then I multiply it by 10 to the 2, which is 10 to the negative 4, which is greater than 5, which is 10 to the 1. So this is going to be less than 5%. So our assumption is valid. So you always want to make sure if you do this assumption, make sure it's less than 5%. If it's not, you'd have to repeat the quadratic. Finally, we can calculate pH. pH is minus log base 10 of the hydronium ion concentration. We know what the hydronium ion concentration is. It's just X. So that's going to be minus log base 10 of X, where X is 3.6 by 10 to the negative 5. So we enter this on a calculator. Remember, in scientific notation, every significant figure becomes a decimal when you log it. So I've got 2 sig figs here. I would need 2 decimals. So this is 4.44 pH. It's an acidic pH because it's less than 7, which makes sense because I have an acid in my equation. So this is a typical example, an exam type problem that you'll see in general chemistry. Next up is a similar problem to the last problem. Again, we have an aqueous ionic equilibria problem. It's an ice table problem. We're given what looks like a buffer initially because we have both a weak acid and its conjugate base. It's a non-ideal buffer because these are not in a 1-to-1 ratio. And we know we're going to shift right because we have a 0 as a product concentration and we have to shift towards a 0 product concentration. So the shift is going to be to the right, so everything on the left decreases by an amount x, everything on the right increases by an amount x. And now we're going to combine the initial and change concentrations to give us the equilibrium concentrations. We are again furnished with the acid dissociation constant. So we're told that this acid, which is formic acid has an acid dissociation constant of 1.8 by 10 to the negative 4. This is equal to the product of the products divided by the product of the reactants. And once again, because of the small size of the acid dissociation constant, it's very likely that we can ignore this negligible shift towards the right, just because the system is so heavily shifted left to begin with. So we're going to assume that that shift is negligible, and this is approximately equal to 0.10x over 0.20. So again, we're ignoring this change by x and this change by x, and we're retaining this value of x. This implies that x is 1.8 by 10 to the negative 4. The 0.2 goes up, so by 0.2. The 0.1 comes down, so the whole thing is over 0.1. We have units of molarity we can apply to the whole structure. and this is equal to 3.6 by 10 to the negative 4 molarity. Again, we've made our assumption, so we should go ahead and verify that that's a valid assumption. Again, we don't need to verify for both numerator and denominator. Just pick the one that's most likely to fail. The one that's most likely to fail is whichever has the smaller number to begin with. So we're going to check our assumption. So 3.6 by 10 to the negative 4 out of 0.1 as a percentage. Again, 10 to the negative 4 divided by 10 to the negative 1 is 10 to the negative 5. Multiplied by 10 to the 2 is 10 to the negative 3. If I've done my math correctly, which is less than 5%. So because that's less than 5%, we have a valid assumption. And make sure that you always show that you've done this check on any assessment whenever you've used the assumption to begin with. Now we can go ahead and calculate the pH. The pH is the negative log base 10 of the hydronium ion at equilibrium conditions. So the pH is minus log base 10 of the hydronium, which is X. So 3.6 by 10 to the negative 4. And this will be 3.44 final pH. In this next problem, we're going to find that we will not be able to use the assumption, and we'll have to go ahead and forge ahead with the full quadratic. So let's have a look. We have ammonia and water to give hydroxide and the ammonium ion. We're given some initial starting conditions. Notice that we don't have a zero. So initially it won't be clear which way to shift. For the benefit of getting through the calculation, I'm going to tell you here that we would shift left. Okay. So I'll tell you that we'll shift left, and maybe we can verify that in a second. But for now, let's just shift left. If we shift left, then everything on the left will increase. And then we combine the initial and change concentrations to get the equilibrium concentration. Okay. So we have those equilibrium concentrations. Now, looking at the equation as written, we know that we have a Brensted-Lowry base as the subject of our expression. The subject is never water, so if we've got a chemical in water, we always try and identify the chemical. In this case, it's a Brensted-Lowry base. So I need the base dissociation constant, not the acid dissociation constant. I'm provided with this value, and I'm told it's 1.8 by 10 to the negative 5. So I go ahead and proceed. This is going to be the product of the products divided by the product of the reactants. And I can solve that. I would FOIL the numerator, so I do first, outer, inner, last. This is going to be equal to, well, I would FOIL the numerator and then I'd solve for one equation, and then I would get the equation in the form of a square. So the final equation would be x squared minus 0.21 plus 0.0020 is 0. And this is a square equation of the form ax squared plus bx plus c equals 0. So now I'm going to proceed, now I have the equation in the square form, I'm going to proceed with the quadratic. So remember the quadratic is x is minus b plus or minus b squared minus 4ac square rooted all over twice a. So it's minus b, so that's plus 0.21, plus or minus the square root of b squared, which is minus 0.21 squared, minus 4 lots of ac. Well, a is 1, and c is 0.0020. I have to square root this expression here, and then divide the whole thing by twice a. The quadratic is going to give me two values, only one of which makes any sense. So x is either 0.2 molarity or x is equal to 0.01 molarity. So there are two mathematical solutions, only one physical solution that makes any sense. You can tell the correct answer, either the correct answer will be the only positive option. In this case, they're both positive. If they're both positive, insert them back into the ICE table and see which one preserves positive molarities. If we were to insert this value, because it's larger than this value, it would return, and it's larger than, well, it's the same as this value, it's larger than this value though, it would return a negative molarity which has no physical significance. So we know there's only one physical solution, so let's proceed with it. And we can go ahead and use the Henderson-Hasselbalch equation. So the pH, this would be not the only way to solve this. You could solve for hydroxide, then you could back calculate hydronium and solve for pH, but it's much quicker since we have it already set to go for the Henderson-Hasselbalch equation. It's going to be the pKa, which is 9.25, plus log base 10, the conjugate base, which in this case is going to be that value, divided by that value, which is 9.68. Okay, so again, we use the Henderson-Hasselbalch equation because it was set up that way. So we've got our base value here. Remember, x is 0.01. If you add 0.01 to 0.5, you get 0.51. That's our base. The acid respective to the base is going to be this one. So 0.20 minus our x value of 0.01 gives us 0.19. So again, we have base over acid. This is the pKa, recall. How would you get the pKa from the Kb? Well, recall the Kb is Kw. So if I wanted the Ka initially, I would say that the Ka is the Kw over Kb. And then once I have the Ka, I would just say that the pKa is minus log base 10 of the Ka. So then I would solve for that. How would we know that it was going to shift to the left? So I told you initially, just assume it does. I'm going to pause the video, erase the board, and then show you how you would know that it's going to shift left. So I've prepared the board here to explain why we knew a priori there was a shift to the left. So we had the initial concentration of ammonia, which was 0.5, the initial concentration of hydroxide, 0.01, the initial concentration of ammonium, 0.2. We would calculate QB and compare it with our given KB, which is a constant. Remember, QB is not a constant, but it follows the same expression. So we calculate QB as the product of the products divided by the product of the reactants, and it returns a value of 0.0040 to two significant figures. We compare that with the given value of KB, and we notice that on this occasion, QB is a lot greater than KB, and that's how we know it shifts left. In general, if you calculate a Q that's greater than K, it implies shift left. If you calculate a Q that's less than K, it implies shift right. This question is a little bit more challenging because we have a mixture of a strong system and a weak system together. Whenever you have a strong and a weak system together, it's a Le Chatelier type problem. And you always address the strong system first. Whenever you have a strong system, notice there's no equilibrium arrow. Equilibrium and ice tables only apply to weak systems. How would I know I have a strong system here other than the single directional arrow? I have a strong base. The strong base is going to interact with this weak acid and shift hard right, and there's going to be no recourse. Whenever you look at a strong system like this, we wouldn't have an ice table. We would have an analog to an ice table, which sometimes I'll call a before added after table or an initial change final table. Regardless of the acronym used, you would not calculate molarity, you would look at the moles of the strong system. So we're told initially we have an ideal buffer. We know it's a buffer because I have a weak Brennstedt-Lowry acid and its conjugate base. In this case, it's acetic acid. And I have a 1-to-1 mole ratio, so I know it's an ideal buffer. I've ignored water because it's a liquid and it doesn't participate in dynamic equilibrium. So I have my buffer initially, and I haven't added any stress, so let the hydroxide be the stress that I'm going to add to my buffer system in equilibrium. So I haven't added any, and now I'm not going to do anything other than add stress. So I'm told that I've added 0.015 moles of hydroxide, and I haven't added any more buffer. Because OH minus is a strong base, it's going to push hard right. It's going to annihilate its equivalent of the weak acid, and it's going to produce product. So there won't be any hydroxide left. It will all have incorporated, it will have deprotonated this H here to make water. And it will take this much away from here. So 0.1 minus 0.015 is 0.085. So again, this quantity minus this quantity is equal to that quantity. And then it's going to generate that much more of this quantity. So 0.1 plus the 0.015 is 0.115. And now I'm going to apply that to my ice table. So we can see that the strong stress, the strong base in this case, has had an effect on the buffer, and it's gone from an initial ideal 1-to-1 mole ratio to a non-ideal ratio. So I'm going to pause the video real quick, set up the ice table, and continue the question. So I've set up the ice table. I've got my final conditions after the stress has been taken care of, and now I want to look at the aftermath on the weak buffer itself. I've got moles here and I've got molarity here. I'm in my equilibrium state now, because I'm looking at the effect on equilibrium. I'm assuming, because the number's the same, I'm assuming a volume of 1 liter. So typically you would have to convert from mole to molarity by dividing by the total volume. Here I've, for simplicity, assumed a volume of 1 liter throughout so that the numbers don't change. Why did I write it this way? I wrote it this way out of preference. I want to calculate the equilibrium pH, so it makes sense to have acid as a product, although this is not essential. I have a 0 on the right, so I know I'm going to shift right. So let's add that. So everything on the left decreases by a value x, everything on the right increases by a value x. And at equilibrium I have 0.085 minus x, I have x, I have 0.115 plus x. I know the Ka value of this system. You wouldn't have to memorize it, it would be provided to you in an assessment, but I'm aware of the fact that it's less than 10 to the negative 4. So I can proceed with the assumption. So Ka is 1.8 by 10 to the negative 5, which is approximately equal to the product of the products. I'm going to ignore the shift x, so just multiply it by this x. Ignore this shift x and just divide it by this x, by this value. So x is 1.33 by 10 to the negative 5 molarity. You would always check your assumption. So if we checked our assumption, we could just go ahead and pick the denominator here because it's the smaller of the two values. So we know that the x is 10 to the negative 5. So 10 to the so this value here, 10 to the negative 5 divided by 10 to the negative 2 is 10 to the negative 3, I think, roughly, multiplied by 100, which is 10 to the 2, is 10 to the negative 1, which is less than 5. So our assumption is valid. Now we can proceed to calculate the pH. pH is minus log base 10 of the hydronium. The hydronium is X, and I know what X is. I'm not tracking that carefully any sig figs, so let's not worry too much about the sig figs in this question. It's about 4.88 pH. Check the validity of your answer. Do I have a weak acid buffer? Yes, so I'd expect a weak acid pH. So this question is how you handle a Le Chatelier type problem where you have a strong stress on a weak system. Cater to the strong system first, looking at moles, and then incorporate it into an ice table for the aftermath as a common ice table. Here we have a second Le Chatelier type problem with different chemicals. Here we have again a strong base, a weak acid, and it's going to shift hard right to give water and the conjugate base. We don't have a buffer this time because initially I just have a weak acid, but I don't have any conjugate base. So there's no buffer present here. We have a strong system, so we set up our before added after table in moles. I don't add any stress initially. I just look at the system that I'm about to stress out, and it just contains 0.004 moles of the weak acid. Now I'm about to add the stress, and I don't add anything else. I purely add 0.004 moles of stress, in this case the hydroxide. It's going to shift hard right and annihilate that much of itself of the base. So it's going to disappear because it reacts in a 1-to-1 mole ratio with HNO2, which is now completely consumed. So 0.004 minus 0.004 is just going to give you 0. But it's going to generate 0.004 moles of conjugate base. So similar to the previous question, I'm now going to pause, set up the ice table, and we'll play this thing out till its conclusion, and ultimately we'll calculate the pH. So returning to conclude this problem now, I've set up my ice table. I've now phrased it based on the only thing that's here. So although conjugate base is on the product side here, it's the only chemical that survived the stress. So it's the subject of my ice table here, so it makes sense to write it on the left. So I put my subject in water and I fill the equation out. I've got zeros as products, so I would shift hard right. Notice now in my ice table, I've got molarity. The number is not the same because in this occasion I don't have 1 liter, I only have 20 milliliters. So when I convert this to liters and then multiply through to convert moles to molarity, I get a different number. So I'm going to shift right. Everything on the left disappears. Everything on the right increases by the same amount. So I get 0.00667 minus x, x. I'm given the Ka value. The Ka is 4.6 by 10 to the negative 11, which is equal to clearly less than 10 to the negative 4, so I can use the assumption. So this is equal to x squared, approximately equal to x squared over 0.0667. So I'm just going to ignore this negligible shift because it's got no force on it. So this implies that x is equal to 1.2 by 10 to the minus 6 molarity. I can check, and in previous questions I've shown you how to check. For now I'm just going to say that we did check and the check was valid. So you should always show the check in your workings. Okay, now we need to calculate the pH. But notice all I know is the hydroxide. I don't know the hydronium. I only know the hydroxide. And actually I've just spotted that I don't need the Ka, do I? Because this is a base. So I should have spotted that earlier. I have my conjugate base. rephrased here as a reactant, so it's a Brensted-Lowry base. So the subject is a base. I'd have to convert the base, the Ka to the Kb. So if I do that, the Kb is 2.2 by 10 to the negative 11. And this is the value I want to use moving forward. So in the question I'm offered a Ka, I quickly acknowledge that I don't need the acid value, I need the base value. So I back calculate the Kb, because Kb is Kw divided by Ka. So I get my Kb value. And actually, let me see what I've done here. Yeah, in fact, what I've written as the Ka value is completely wrong. So my apologies for that. So I just use the Kb value. Okay. I have a value of x. I now need to solve for POH, because that's all I can do. So POH is negative log base 10 of OH minus, which was x, so I can plug that value in. 1.2 by 10 to the negative 6, which gives me a value of 5.92. But that's the POH. I need the pH. Well, I know the pH is 14 minus the POH, which is 14 minus 5.92, which is approximately 8.08. Does it make sense? Should a base have a pH greater than 7? Yes. Had the student rushed in and not realized this was a base, and not realized they should have used the Kb, they would hopefully have realized that a pH value of 5 doesn't make sense for a base. This next question is a slightly different type of question that you'll see in ionic equilibrium type problems, and that's solubility. So in the first semester of a general chemistry class, you learn things like insoluble and partially soluble and completely soluble. And in the second series of general chemistry, you realize that everything can be quantified, and really there's no black and white delineator of soluble or insoluble. You can just have a very low solubility. So here we have iron 2 hydroxide, which is typically labeled as insoluble, but we're going to quantify what we mean. If it did split up, it would be as an equilibrium system to give its cation and its anion. I'm going to quantify the solubility by performing an ice table. An ice table is appropriate, but because we know it's insoluble, its equilibrium constant should be less than 1. So it's a weak system, so an ice table is appropriate. My reactant is a solid. Solids don't participate in dynamic equilibrium, so I can ignore them and I can focus on just the products. Initially, if it's a solid and I haven't done anything to it, we'll assume there are no free ions. So I just take a solid object, there are no free ions in a solid object. Now I'm going to add water to it and see what concentration of aqueous ions I can produce. So clearly I can't shift left because there's nothing as a product to shift left with, so I have to shift right. Historically, they call the shift S, although it just means X. So we'll stick with the historical use of the symbol S, but again, it's just the regular shift quantity X. Notice this is a 1 to 2 mole ratio, so I actually need a coefficient 2 here. At equilibrium, we add them, so 0 plus S is just S. Here, S stands for solubility concentration. And here I have 2S. The equilibrium constant for an insoluble product is called the solubility product constant, KSP. And I know that's the product of the products multiplied by the product of the reactants. But the reactants are not represented here because they're a solid. So I just have ion 2 multiplied by hydroxide squared. Remember, the coefficient 2 becomes an exponent 2 here. So that coefficient becomes an exponent. So my value of ion 2 is S. My value of hydroxide is 2S, but I've got to square it. So notice that molar coefficients impact our calculations twice. The coefficient itself becomes a coefficient. The coefficient also becomes an exponent. So don't forget to use the coefficient twice. So the square hits the 2 and it makes it a 4. So this whole thing equals S by 4S squared. So this whole thing is equal to 4S cubed. So S by 4S squared is 4S cubed. So if I solve for S, S is the solubility product constant divided by 4. And then to get rid of the cube, I would cube root the whole thing. So raise it to the 3rd power to cube root. You would be provided with the KSP value. There's no need or way that you could memorize that a priori. So 4.87 by 10 to the negative 17 divided by 4, all cube rooted. So S is 2.30 by 10 to the negative 6 molarity. Notice, this is 17, sorry, not 7. Notice that the solubility product constant for this chemical was 10 to the negative 17. So again, in an earlier sequence of general chemistry, you would just say that that's insoluble. In a later sequence of general chemistry, you can actually quantify, well, how insoluble is it? And this is how you do a solubility product type question. Here's a second example of a solubility product constant type question. We're given silver bromide and we're asked to calculate the solubility product constant given some information about the solubility itself. Okay, so we have no participation in dynamic equilibrium from a solid, and initially we haven't added water, so we can assume there are no free ions. We have to shift right because we always shift into a 0. Because these ions are in a 1-to-1 ratio, we'll have an increase by a quantity of S, where again here S historically was just used instead of X. At equilibrium we add them, so I have S and S. So I know that the solubility product constant is the product of the products, which in this case is the 1-to-1 ratio of free ions, which is S squared. And in this question I was provided with the solubility value S. So again, in this question I was furnished with S. Typically you'll either be given S and asked to solve for KSP, or vice versa, you'll be given KSP and asked to back calculate S. So because I knew what S was, I square it and I was able to calculate KSP. This final example of a solubility product question is a common ion type question, where instead of no initial ions prior to solvation, we actually have a common ion. So here we already have calcium ion dissolved before we add the calcium fluoride. So we have a common ion, but otherwise we proceed as usual. We would shift right into the 0. So we have plus S plus 2S. 2 because there's a coefficient 2 over here. At equilibrium we add them, so we've got 0.25 plus S, and I've got 2S. In this question, I'm given the KSP value. I'm asked to solve for S. So the solubility product constant KSP is going to be the calcium concentration and the fluoride concentration squared because of the coefficient 2 here. Now I plug my values in. I can use the assumption, I can assume that the shift is negligible because I'm offered a K value that's a lot less than 10 to the negative 4. The K value I'm given, incidentally, is actually 1.46 by 10 to the negative 10. Again, knowing that this is so much smaller than my cutoff of around 10 to the negative 4 allows me to assume I can make the assumption. Okay, so this is going to be 0.250 by 2S squared, roughly. Again, I'm ignoring this S, and I'm taking 2S and I'm squaring it because of the coefficient 2 here. KSP is 1.46 by 10 to the negative 10. So this implies that S is 1.21 by 10 to the negative 5 molarity. Again, this is a common ion example of a solubility product constant question. So to summarize, we've just seen approximately 8 questions looking at aqueous ionic equilibria and the type of problems that you should practice ready for an assessment in general chemistry. The calculations were broadly 3 types. We looked at just regular ice tables and calculating the pH and the pOH based on the equilibrium concentration. We saw usage of the Henderson-Hasselbalch equation. You never actually have to use the Henderson-Hasselbalch equation, but you can use it. It can be a time saver. Whenever you do use the Henderson-Hasselbalch equation, make sure that you are using only the equilibrium concentration of acid and base. Even though the shift is small, don't use the initial concentration, because if you show workings that way, you'll get penalized. So many people do. It's wrong. Don't do it. Then we looked at Le Chatelier type problems where we have a combination of a strong stress on a weak system at equilibrium. And we saw that we have to use a before added after table, or you could call it an initial change final table. We cater to the strong component first. We calculate the moles, what it will do, what are the net moles, what's the aftermath in terms of moles based on the strong system. And then we apply it to the weaker system at equilibrium and we convert back to concentration. And then finally, we looked at solubility product constant type questions. They come in 3 flavors, I guess, or rather 1 flavor with 3 potential sub-questions they can ask you. You're either going to be provided with the solubility product constant KSP, and asked to calculate the solubility S, or vice versa, you're given the solubility S, you're asked to back calculate the solubility product constant KSP. Or you could do both of those things for a common ion type problem, where initially you have something dissolved anyway, and you're just adding an insoluble product with a common ion. In this case, I had a common amount of calcium added to an initial concentration of calcium. So that concludes this video on aqueous ionic equilibria practice problems.